In the year 2000, a research vessel drifting above the mid-Atlantic ridge sent a camera down into total darkness, 700 meters below the surface, and caught something that made the entire team go quiet. Not a shipwreck, not a new species, a skyline. Pale white towers rising 60 meters off the seafloor, taller than most buildings on land, standing in a part of the ocean where nothing should be standing at all. No volcano nearby, no magma chamber underneath, no sunlight for miles. And yet, this structure had apparently been alive, in some sense, for over 120,000 years. Longer than modern humans have painted on cave walls. Longer than the last ice age has been over. Scientists named it the Lost City, and almost 25 years later, it remains one of the strangest places ever found on this planet. The expedition that found it wasn't even looking for something like this. Researchers were mapping an underwater mountain called Atlantis Massif, roughly 15 kilometers off the main spine of the Mid-Atlantic Ridge, when sonar picked up formations rising far higher than the surrounding seabed. When the submersible cameras got close enough to make out detail, they found spires and pinnacles built from pale carbonate rock, some no taller than a person, others soaring 60 meters into the water column, roughly the height of a 20-story building, standing in complete darkness under crushing pressure. Here's the problem this discovery created. Before 2000, marine geologists had a tidy explanation for how life could exist in the deep ocean without sunlight. Volcanic hydrothermal vents, called black smokers, punch through the seafloor near tectonic boundaries, spewing scalding, mineral-rich fluid that can reach 400 degrees Celsius. That superheated chemistry feeds bacteria, which feed tube worms, crabs, and shrimp, in ecosystems first documented in the late 1970s. It was strange, but it fit a pattern. Heat from magma equals energy equals life. The Lost City broke that pattern completely. Its vents run cool, somewhere between 40 and 90 degrees Celsius, gentle enough that a hand could survive brief contact with the outflow. There's no magma driving it. There's barely any volcanic activity in the region at all. So the question became unavoidable. If it isn't heat from molten rock powering this ecosystem, what is? The answer turned out to be a reaction most people have never heard of, called serpentinization. Deep beneath the Lost City sits mantle rock, the layer of earth normally buried far below the crust, but here it's been pushed up close to the seafloor by the slow spreading of tectonic plates. When seawater seeps down through cracks and comes into contact with that mantle rock, a chemical reaction begins. The rock absorbs water and transforms, releasing heat, hydrogen gas, methane, and highly alkaline fluid, with a pH that can climb past 11, nearly as caustic as ammonia. That fluid rises back up through the seafloor, and when it hits the cold, slightly acidic seawater above it, calcium carbonate precipitates out and hardens into rock, layer after layer, decade after decade. Over tens of thousands of years, those layers built the towers explorers found in 2000, some collapsing and rebuilding, one still standing 60 meters tall, nicknamed Poseidon. The entire skyline is essentially mineral scar tissue from a chemical reaction that never had to stop, because it isn't burning fuel, it's just rock meeting water. What makes this especially strange is the timescale involved. A black smoker vent can burn itself out in a matter of decades, once its underlying magma chamber cools or shifts. Serpentinization doesn't work on that clock. As long as fractured mantle rock keeps meeting seawater, the reaction keeps producing hydrogen, methane, and heat, with no fuel source to run dry. That's the mechanism researchers believe has kept the Lost City active for over 120,000 years. A chemical engine that doesn't need to be refueled, only fed by the ocean itself. To understand why this location exists at all, it helps to understand the Mid-Atlantic Ridge itself. Running down the center of the Atlantic Ocean is a nearly 16,000-kilometer mountain range, mostly hidden underwater, marking the boundary where the North American and Eurasian plates, and further south the South American and African plates, are slowly pulling apart. As they separate, magma rises to fill the gap, cools, and becomes new ocean floor, pushing the older crust outward on either side. This is how the Atlantic Ocean has been widening for roughly 180 million years, a few centimeters a year, about the speed fingernails grow. Most of the ridge is defined by that constant volcanic activity, which is exactly why the black smoker vents form there. But the Lost City sits about 15 kilometers off the main ridge axis, on an underwater mountain called Atlantis Massif, in a spot where tectonic stretching has thinned the crust enough to expose mantle rock directly to seawater, without any accompanying volcanism. It's a geological accident of location, a pocket where the plumbing works completely differently from everywhere else along that same 16,000-kilometer chain. That difference in plumbing changes everything living there. Black smoker ecosystems are famous for giant tube worms, some over 2 meters long, clustered around the scalding vent openings, along with dense colonies of crabs and shrimp packed around the hottest fluid. The Lost City has almost none of that. Instead, the dominant life forms are microbial mats, dense communities of archaea and bacteria that coat the carbonate structures in white and orange films, feeding directly on the hydrogen and methane produced by serpentinization. Snails, crustaceans, and sea urchins are present, but this is fundamentally a microbial world, not a giant invertebrate one. It runs on chemistry alone, a process scientists call chemosynthesis, where energy comes from chemical reactions instead of sunlight-driven photosynthesis. For biologists, this distinction matters because it shows that hydrothermal ecosystems aren't a single template repeated across the ocean floor. Change the underlying geology, and the entire food web changes with it. From towering worms feeding on bacteria at scalding vents, to microbial films quietly coating cool carbonate towers a few dozen kilometers away. Two ecosystems, both running on chemistry instead of sunlight, built by completely different geological processes. That single fact is why NASA has paid such close attention to a hydrothermal field most people have never heard of. Two of the more compelling candidates for life beyond Earth are Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Both are believed to hide liquid oceans beneath thick shells of ice, oceans that have never seen sunlight and never will. If life could exist there, it would need an energy source that has nothing to do with a star. The Lost City is the closest working model we have of exactly that kind of system: rock, water, and chemistry producing energy in permanent darkness, with no volcanic engine required. Researchers studying serpentinization on Earth are, in a very real sense, rehearsing for a mission that hasn't launched yet. There's another reason this site matters, one that reaches back further than astrobiology. The reaction happening at the Lost City produces hydrogen and simple organic molecules under alkaline, mineral-catalyzed conditions, an environment some origin of life researchers consider a strong candidate for where the first chemistry of life on Earth may have begun, long before oxygen filled the atmosphere. If that theory holds, the Lost City isn't just a strange curiosity. It could be a living, still running example of the exact conditions that got life started on this planet nearly 4 billion years ago. Given how significant this discovery is, you'd expect scientists to have found several more sites like it by now. They haven't. Since 2000, researchers have identified other serpentinization-driven vent fields elsewhere in the ocean, but none have matched the Lost City's specific combination: the scale of its carbonate towers, the age of the system, and the particular geological setting that allows mantle rock to sit exposed near the surface without volcanic interference. Every other candidate found so far has been smaller, younger, or chemically distinct in some way. As far as marine geology has been able to determine, the Lost City remains functionally one of a kind, a single, unrepeated experiment in how a planet can build life-supporting chemistry without fire. And that uniqueness is precisely what makes its current situation so uncomfortable. The Lost City sits near mineral-rich sections of the seafloor that have drawn growing interest from deep-sea mining operations, searching for cobalt, nickel, and rare earth elements used in batteries and electronics. Mining machinery working nearby, or directly across the Atlantis Massif, could damage or destroy carbonate structures that took over 100,000 years to form, structures that cannot be rebuilt on any human timescale once broken. Marine scientists have specifically flagged the area for protective status, arguing that a site this rare, this old, and this scientifically important should not be treated the same as an ordinary patch of seafloor. The difficulty is that international regulation of the deep seafloor is still catching up to the technology now capable of reaching it. Large stretches of the mid-ocean floor fall outside any single nation's direct jurisdiction, governed instead by international bodies still working out exactly which areas deserve permanent protection. A site can be scientifically irreplaceable and still lack the legal status that would stop a mining claim from being approved nearby. That gap between what scientists know about the lost city and what regulators have formally protected is exactly where the real risk sits. What makes this urgency real is how little we've actually learned so far. Only a small number of expeditions have ever reached the lost city, and each one has returned with new microbial species, new insight into the serpentinization process, or new evidence about how long the system has been active. Every unexplored corner of that white skyline is still a question mark. Losing it to mining before it's fully studied wouldn't just erase a geological formation. It would erase a working model for the origin of life on Earth, and quite possibly, our best real-world reference point for finding life somewhere else entirely. 25 years after that first camera drifted through the dark and found a city that had no business existing, the lost city is still teaching scientists things they didn't know to ask about. It's rewritten the rules for what counts as a habitable environment. It's given NASA a working blueprint for icy moons millions of kilometers away, and it may be quietly holding the answer to how life began right here, on this planet, in the dark, without a single ray of sunlight involved. Think about what that really means. A single mountain on the ocean floor, sitting slightly off from where geologists expected anything unusual, has managed to reshape three separate fields at once: how we define habitable environments, how we search for life on other worlds, and how we picture the earliest chemistry on this one. Very few places on Earth carry that much scientific weight while remaining almost completely unknown to the public. If a discovery like this deserves to survive long enough to be understood, that story needs to keep being told. Subscribe if you want to keep exploring the deep ocean discoveries most people never hear about. Drop a comment with which part of this shocked you the most, and stick around, because the next find down there might rewrite the textbooks all over again.